Well, our project is about development of a home-based handheld fetal heart rate monitor. We all know that a fetus is an unborn baby or one that is still within its mother's womb. And the heart is one of the earliest organs to develop in a fetus. Did you know that within the first 3 weeks after conception, you can actually hear the first heartbeat of a fetus? Therefore, the heartbeat is an important parameter in knowing how healthy a fetus is, or the kind of pregnancy you're dealing with, whether it's a high-risk pregnancy or it is just a normal pregnancy. And in our problem statement, we did research and we found out some of the already existing ways in which this heart rate is being monitored. And one of those is using a peanut stethoscope or a fetoscope. And being in an undeveloped country like Uganda, that one is one that is used largely because people can't afford the other expensive devices. And we noticed that with this device, there is a lot of inaccuracy because in noisy areas you don't get very correct results, and in a place where you're in a situation where the fetus has changed its position, you may not actually easily detect the heart rate well, or under circumstances where it's a high-risk pregnancy and the fetal heart rate is very low, you will not be able to hear it. And it also does not give you a visual picture for you to know the exact curve. Therefore, we notice that there is a great need to have a device that is cheap, that is portable, and that is easy to use by not very trained people like pregnant mothers, like caretakers of these mothers, like nurses that are not highly trained to use these technologies. Therefore, our general objective is to make a fetal heart rate detection system, and some of our specific objectives is to make one that has a visual display of the heart rate, one that can monitor the heart rate from the first days to the end of the pregnancy, that does an entire detection of the entire process. Also, we intend to be able to monitor high-risk pregnancies with our device, and also to be able to help mothers who are not able to afford constantly going to a hospital to get their heart rate checked, to be able to do it from home in case there is an emergency that needs to be looked at. Thank you.
I'm going to talk about the code for the home-based fetal heart rate monitoring system. So the first part of the code, we have declaration of the pins where the LCD, red LED, green LED and alarm are attached on the Arduino. The LCD is attached from pin 2 to 7, the red LED is attached to pin 9, green LED is attached to pin 8, and the alarm is attached to pin 10. The void setup, this one it's for initialization of the output. In this case, we have 3 outputs. We have the red LED, the alarm, and the green LED. Yeah. Then the void setup also declares the screen size. In this case, the screen size, it's, as you can see, it's a 20 by 4 screen. It also outputs a simple message to notify the user that the screen is powered and can be ready to receive the input soon. So the simple message it will output is the Dear Project Fetal Heart Rate Monitor by Isaac, Cynthia, and Precious. Then we have the void loop. The void loop picks an input signal via pin A0 on the Arduino. Then we have the formula for calculation of the heartbeats. It's a float because it can be in decimal places, so it can be a decimal, so that's why it's a float. It's used for this is the formula for calculation of the heartbeat from this signal acquired from pin A0. So then we have the if loop. This one, if heartbeat is in the normal range, that's between 110 to 160. We shall have the green LED light and the alarm will beep once and the results are shown. So for any inquiries, you ask the doctor. Then in case the heartbeat is abnormal, it's outside the normal range of the fetal heartbeat, that's outside the range of 110 to 160, so it can be either low or it can be very high. An emergency action will be displayed. The red LED will light, the alarm will beep continuously, and you will need to, I think an emergency action is required immediately, and it will keep beeping. Thank you. For us to run this code into Proteus simulation, we shall first have to verify it. After verification, we shall copy the file location and paste it on the Arduino Uno in the Proteus to upload it such that it can run in the simulation.
Okay, I'm going to take you through the circuit part that we divided into 5 parts. We have the first step, which is acquiring the signal. We have the second step, which is amplifying the signal. The third one is filtering the signal. Analyzing or processing the signal is the fourth. Then the last one is display of the output. So we are going to start with the first one, which is acquiring the signal. And this is the circuit, the first circuit, but then we're going to look at the entry point where we decided to use a condenser microphone to acquire the signal. It acts as a sensor to detect and acquire the fetal heart sound. A condenser microphone can respond to sounds of all frequencies up to 20 kHz, and the frequency of the fetal heart sound is up to 200 Hz. So our cutoff frequency will be 200 Hz. So before, like in our proposal, we had decided to use the ultrasound Doppler sensor to acquire the signal. However, we changed because using the ultrasound Doppler technology would require several pre-made components, and its circuits are very complicated compared to the time period that were given. So we decided to use the condenser microphone. But here, since we don't have a condenser microphone in Proteus, we decided to use a potentiometer. So the signal from the potentiometer is fed into the second step of the circuit, which is amplifying the signal. So we used, in the amplification circuit, we used Proteus to build one, and then a preamplifier is used to prepare a signal from the microphone to be further amplified, filtered, and processed. A low noise audio OP amp, which is NE, as you can see it is NE5532, was chosen because it has a high open loop gain of about 60 decibels, and therefore it is more linear, and the output voltage is more proportional to the input voltage. Then we also connected a few capacitors and resistors, as we can see, and then the output from the op-amp leaves the op-amp through a potentiometer. Then it is fed into the next step of our circuit, which is the filtering step. So the signal from the pre-amplification circuit is then fed to the filtering circuit. In order to remove the noises, a filter is used. By attenuating high frequencies, the signal of the heartbeat is being increased relative to the noise, and in that case, a low-pass filter has to be used. We used the Butterworth fourth order filter because it has the least amount of attenuation over the pass region of the filter, resulting in least distortion of the signals that were passed. Yeah, so we can see like this is a Butterworth fourth order filter. So in this Butterworth fourth order filter, there are two Salem key filters. We can see this is the first one and this is the second one. We used two in order to improve the gain roll-off of the response. The gain roll-off response means that if we improve it, it means that the signal above the cutoff frequency will be reduced at a larger magnitude, and therefore we'll be able to come up with only the heartbeat. All the other distracting sound and noise will be removed. And as I informed you before, the cutoff frequency is 200 Hz. Therefore, to select the appropriate op-amp used in the filter, the unity gain bandwidth was the most important characteristic, and therefore we chose the LM741 op-amp. So as we can see, this is like a unit gain op-amp. Yeah, so there are two, but we use the LM741 op-amp. Then we connected resistors, capacitors. Yeah, at first we had used one stage, but then like the signal we're getting was not that clear, so we decided to add another one. So that the result were two Salem key filters. Yeah, so the output from the filtering circuit is then fed into the Arduino Uno, where we used Arduino Uno R3, and this is to process the data. So the signal input is in analog form, so it can be connected to the analog input in the analog input pin at the Arduino Uno. Here we used an A0. So you're going to upload the code into the Arduino Uno and then run. So as we can see, the fetal heartbeat per minute is 124, which is within the normal range, and the green LED is lighting. So when the input is increased above 160, we can see that here the fetal heartbeat per minute is 169, which is not within the normal range. The red LED will light to go on, and then also the buzzer will be continuous, meaning that emergency action will be required. When it is decreased below 110, as you can see on the screen, the heartbeat per minute is 102, which is below 110. You'll see that the red LED will light and the buzzer will be on continuously, meaning emergency action will also be required.